Now let us move forward to our next speaker, Romaniello Martino. Sorry if I am messing with the pronunciation. He is from the European Southern Observatory, is stationed in the headquarters in Garching. His main field is studying Cepheid stars as a high precision tool to determine cosmic distances, for example, expansion of the universe. And today he will be talking here, the universe speaks for itself, from unsupervised physics to semantic source separation. Let's welcome Martino.
So I'm presenting this on behalf of the people you see listed here, who have done most of the work, in fact, and especially Nima Sedagat, the second name you see there. He was supposed to do the presentation himself today, but then meanwhile he has moved on with his career, so I'll do the presentation instead, and I'll try to do justice to the work we've done. So, the work we've done is part of ESCAPE, and Marco Molinaro has already presented ESCAPE in his presentation a while back this morning, so I'll just do a quick thing here. So it's a big European collaboration funded by the European Commission to bring together particle physics and astronomy in sharing data. And the wider context is what in Europe we call the European Open Science Cloud, which aims at providing an infrastructure to do so in the future, infrastructure and content to do so. As it were, ESCAPE has several work packages. You see them listed here. The details don't particularly matter here. You know, they cover all sorts of tools needed to do this, to share data in a fair way. And I'm going to talk about especially this pink corner down here to the right-hand side, so adding value to trusted content to the archive. This is what I will be focusing on. This is what we've been doing at ESO for ESCAPE. So what we've been trying to do is to explore applying deep learning techniques to enable searches in the ESO Science Archive. Okay, so this is the headline of what we've been trying to do. Why is that? So these are two screenshots from the ESO Science Archive, the Science Portal, and you see that when you log there, the one on the left is a landing page, you're not presented with anything specific, you're presented with the whole content of the archive. The celestial sphere is color-coded and also in grayscales, depending on the type of observations we have in every position on the sky. These are just heel pix bits. So how do you go from there to the sources you're interested in? And you see we have of the order of 4 million assets. So how do we allow people to find what they need? So we're allowing searches based on the physical properties of the data rather than the technical description of how they were observed. This is probably too small to see, but we have facets, and what we expose to users are quantities like signal to noise, or depth of an image, or the resolution, spatial and spectral, so that they can find the data they're looking for their own size. It's not necessarily based only or primarily even on position on the sky, but really on a physical description of the properties of the data. We also expose more traditional searching criteria, but and we're trying to find a balance between the two. What we're trying to do now is to move even further and really into the properties of the data itself. So first thing in order to do that is to characterize the data at a proper level. And this is what we've been trying to do with deep learning. The first two bullets are what I just said earlier, so it's just for the record. Let me just use a second on the last bullet there, let the data speak for itself. What we've tried to do is not to impose any of our preconceptions of what the data look like, but let the machines find that out. And that is both on practical reasons, because there's just too much data for us to know the content, and also because we don't want to do that. We want users to do their own science, not us imposing our preconceptions on what users might be able to do or not. So we try to have the machines explore the archive without any preconception. And we started as a case study from stellar spectra. So the instrument of choice was HARPS because it had a large archive of the order of 300,000 individual spectra. each with of the order of 300,000 wavelength channels. And we've done it in two ways. We've collaborated with HITS in Heidelberg with this. They chose a fully connected autoencoder with two latent dimensions. And this is very agile architecture, which is great for speed and interactivity. Well, we are at ESO. We've tried another approach with a fully convolution, fully connected layers with latent dimensions in the middle, and trying to, without degrading the spectral resolution, trying to figure out what the network learns. And this is what I'm going to concentrate on in the next few slides. After the machine has done its job, we need to turn this into something that's useful for humans. Okay? Otherwise, there's no point in it. This is not an exercise in computer science. This is an exercise in making archive services for users. So we need to ask ourselves, what makes two spectra, in this particular case, two assets, two archive assets similar? Can we assign some physical meaning to what the machine found? And how do we present these results? Okay? And we want to make these services for a larger community as possible. Because half of the, broadly speaking, half of the astronomical community out there uses the ESO Science Archive. That's our target, okay? Not the few who know what machine learning is. So, well, this is just a slide that says, we don't want to do the machine learning, we want to do deep learning because we don't want to impose what the features to be extracted. Let's see if the machine learns it by itself. Okay? So let me move on. This is the design. It's pretty straightforward. We start on the left with our signal. That's the spectrum in this particular case, which is turned upside down here. It's the dimensionality. It's reduced to the middle, the latent space, and then reconstructed again. The reconstruction and input are compared until they're done properly. The reconstruction is proper. And that's when, at the end of this process, the machine has learned. And let's see. This is just an illustration, if the thing plays, of how the machine learns. At the beginning, it starts without knowing anything. I'll just speed it up a little bit. And then it starts to figure out, okay, there's something out there. And then it starts refining this something. It figures out that there are, the certain point, it figures out that there are lines, sharp features in the spectrum, et cetera, et cetera, et cetera. It deepens them until it finds a satisfactory match. Okay? Now, we started out with 128 dimensions in the latent space. And the machine figures out that not all of them are significant. And by the way, we're imposing some disentanglement to make this interpretation easier. Okay, but only 6 dimensions out of the 128 we started from carry some meaningful information. Okay? The machine has learned something not trivial. What is it that it has learned? Can we interpret that? If we now plot on the x-axis are just the number of the indices in the latent space from 1 to 128. And we try to see if those 6 dimensions correlate with known stellar parameters. Radial velocity, effective temperature is going in vertically, gravity, metallicity, and Hermes. And you see that in 3 cases out of 6, it does. The network picks up, that's the second from the top, that effective temperature is a meaningful physical characterization of a spectrum. And so is surface gravity. We didn't say anything to the network about any of this. It's not trained to do this, but it did it by itself. On the other hand, it's sort of, we note, but it's sort of disappointing that metallicity, so the chemical composition of the star, is not picked up as a particularly significant dimension. Okay? And we've published this in a paper a couple of months ago. Just a quick note, if we had done the same analysis with simple PCA, the spectra would be reproduced, of course, because PCA is a unique, provides a unique description, a full description of the input, but it doesn't pick up any specific dimension. So in this sense, the PCA is not learned. It can reproduce the spectrum, but without learning any of its characteristics. Okay? So this is where we stand basically on this. The basic idea works. The network figures out that there's something important going on there, and it figures out some of the physical characteristics of the spectra. Some of them it doesn't. We're not exactly sure why. There may be several interpretations. So there's something we need to explore. So a couple of words on another thing that the network seems to pick up. So the network picks up intrinsic astrophysical signatures from the telluric absorption created by the Earth. Okay, so this is one spectrum. The blue is the input, and you see that the network has not reconstructed some of the features in this network. This is the orange one. It does not follow the blue input in some cases. And that's good, because that is input that we're not particularly interested in as astronomers, because that's a signature of the Earth atmosphere, not of the stellar source, of the astrophysical source. So we explore this. We bumped into this by chance, to be honest with you, but then we start to explore this, and so we explored why and how a network under circumstances picks it out without being asked to do so again. So the network understands the semantics by itself, and it turns out that the crucial thing here is that it learns it for as long as you're not in the topocentric reference of frame, or frame of reference for velocities. That's the frame of reference that's addressed with respect to the observer, which is a very special frame of reference. If you are in any other frame of reference, so the ones that are useful for astronomy, the network picks up this difference. And you see there how it reconstructs certain features on the right-hand side. So the stellar ones, without reconstructing the telluric sequence, okay? And we're trying also to work out the consequences, also the practical consequences. We're doing that because, of course, the telluric signal is a nuisance to the astrophysical interpretation of the data. Last couple of things. Alma, we've moved to the next data type. Alma generates, so this is an array, it's a radio telescope, it's an array, millimeter and sub-millimeter. Generates 3D data cubes, 2 spatial dimensions and 1 spectral dimension. What we want to do is to analyze the cubes as they are, 3D. But they're not, as a first step, they're not homogeneous enough to expose them to the machinery directly. So we started with 2D images, so collapsing the spectral dimension. And we're running them through the same machinery as the spectrum, and this is a work in progress. Then we started to build also user tools on top of, user tools on top of the results to try to expose this, and these are just prototypes to give you an idea. So the first one is sliders where you change the weights in the deep learning latent space, and these are the 6 significant dimensions you see here on the left-hand side. And with sliders, you see how each dimension affects the output. So this is a way for users to figure out what is it that the network has learned and make up their mind if it's useful for their specific use case or not. So this particular slider changes the shape of the spectrum, as you can see in the 2 middle figures, well, the figures on the right-hand side, at the center here of the slide. This slider changes the shape of the spectrum. This other slider here changes the position of the lines. It does not so much affect the depth or the lines of the shape of the spectrum, but their position. So this is the data dimension that picks up radial velocity. Okay? Then this other one changes the shape of the lines. You can see this in the right-hand side, in these 2 figures. Sliding this slider changes the shape from very narrow to broad. And this, again, are ways to explore what the machine learned and make up for yourself, as on user side, whether this is useful for what you want to do with the data. Okay? The other service we're exploring is a similarity search. The idea here is that you as a user, you upload the spectrum you're interested in, and the machinery tells you spectra that are similar to the ones you've uploaded. Okay? And this is a way to skim through the 4 million assets that are in the archive and pick the ones that resemble the one that you as a user are interested in whatever characteristics you're interested in. And that's why you also need to have tools, and that's the thing on the right-hand side, to explore what are the characteristics that the network picked up and made a comparison for. And then you can choose which dimensions, and then you need tools previously to understand what dimensions mean, and we also are developing this connection. I guess that this is what I wanted to say to you for today. So thank you very much, and with this I will stop sharing.
Thanks a lot, Martino. It's really tremendous work, and it's a nice tool. And now we have time for one or two quick questions. One we already have on our Discord channel by Michelle. And she says like it's a very interesting work, and asking, did you find the architecture of the auto-encoder had an impact of the correlation with physical parameters?
Okay, here I'm a bit out of my turf because I'm the astronomer in the situation. So, and again, Nima would have had a better answer than what I can provide, but let me try. Yeah, there are characteristics of the network that influence the output, but not dramatically so. I mean, the fact that basically out of the data set, 6 dimensions are picked up, stays whatever it is that we do, and also the ones that are picked up. We tried to play with its characteristics of the network to see if, say, chemical composition would be picked up, but we didn't manage to do that. So there are, at the fine level, yes, but at the bigger picture level, basically this is what these types of networks pick up.
Perfect.
I hope this answers the question.
Yeah, perfect. Hope. Do we have another last question for Martino on this live channel? Okay. If not, then we can have a further discussions on our dedicated Discord for this particular talk. Let's thank speakers.